Hello, and welcome to Chapter 9, where we're going to be looking at monoprotic acid-base equilibria. The next few chapters we're going to be looking at are all focused on acid-base chemistry with the goal of understanding acid-base titrations. So Chapter 9, we're going to look at monoprotic acids and bases. Chapter 10 will cover polyprotic acids and bases, building on what we go over in this chapter. And then Chapter 11 will apply that to acid-base titrations. So when we're thinking about monoprotic acid-base equilibria or any acid-base equilibria, one of the big questions we often are trying to figure out is, if we know the concentration of a acid or base in a solution, what's the pH? And that's one of the most common calculations we're going to be doing is, given a concentration of, say, a weak acid like HA is our generic weak acid, what is the pH? Now, this is obviously going to depend on many factors, but that's the main thing we're going to look at. But in the first video here, we're going to look at the simplest case, which is actually not a weak acid, but instead it's a strong acid or base. And finding the pH in these cases is pretty straightforward. So let's say we have HBr. This is an example of a strong acid, or maybe this is HCl. It doesn't really matter. Let's say we have a 0.10 molar solution of HBr. And the question is, what is the pH of this solution? So I want you to pause the video, think about this, see if you can come up with an answer. This is not a trick question. It is as simple as it seems. Okay, because this is a strong acid, that means our HBr completely dissociates, right? This is not an equilibrium. K is very large, and the acid completely dissociates into H plus and Br minus. That means that our concentration of H plus is equal to 0.1 molar. And by the definition of pH, we can just plug in that pH is the negative log base 10 of the hydrogen ion concentration in water. More accurately, it's the activity, and we'll get to that in just a second. So we get negative log base 10 of 0.10 molar, which is equal to 1. And so the pH of a 0.1 molar solution of HBr is 1. Now, the more accurate version of pH, of course, is that pH is equal to the negative log base 10 of the activity. Let me use the right A here. The activity of H plus. And so we should make a correction here, including the activity coefficient. Let's go ahead and do that. We can actually, H plus is on our list. So if we go to table 8-1 from our previous chapter, we can see that gamma for H plus at a 0.1 molar concentration, or more accurately, a 0.1 molar ionic strength, is equal to 0.83. So that means that activity of H plus is equal to the activity coefficient times the concentration of H plus, which gives us 0.83 times 0.10, or that the activity is 0.083. All right, we can plug that into our pH calculation here. Negative log base 10 of 0.083. And we get a pH, if we plug this in, we get a value of 1.08. So it does make a difference, but it's not a large difference. And largely, we will ignore activity coefficients throughout this chapter. Because, again, it makes a difference, but not a very significant one. And generally, in these sorts of calculations, we want to get approximate values. We're not trying to get, down to, the nearest decimal, hundredths place in the pH value. So this is an example, this is the simplest case, strong acids, strong bases. We can just look at the concentration of H plus directly from the dissociation of our strong acid or strong base.